This is ENME 351, Lab 4, Sampling and Aliasing by Garrett Schweitzer. So I have my timing loop here. So first I'm reading in the value for my potentiometer. Then I'm going to convert that into a time. Then I'm basically checking the current elapsed time minus whenever this if statement was last executed, if that's greater than the time. And then I will be changing the last read time to update that to the most recent, and then I will be reading in the value output from the end scope and then printing that every time this if statement executes. This is my collection of screenshots from my collected data, and the table over here is my data table. So this is going to show in blue the sources that do not show any signs of aliasing, and in red those that do. So for here, at a sampling rate of 500, the only thing that showed aliasing was our 300 Hertz source. So this graph here, and I could quickly go through these and you can see, based on the table for yourselves, those which showed aliasing. So for 500 Hertz sampling rate, 200, 142, and then 100. This is my data table for exercise 1. As you can see, the theoretical and experimental values for 75 Hertz and 100 Hertz were pretty accurate, but some of them started to drift away in 215 and 300. Some of these are quite different from what I would have expected. But overall, my data was a little noisy, and I'm not exactly sure what introduced that variance into my data. This is how I calculated my theoretical alias frequency using this formula I made here. So if our sampling rate is less than double our source frequency, we're going to go through here and actually truncate. Well, if it's even, the ratio is even, we are going to then go one way up the folding graph, and if it is odd, we're going to go the opposite direction of the folding graph. So for one, we subtract one, for one, we don't. So we're left with the decimals after the ratio, and then we can multiply that by our frequency, source frequency here, and then we can obtain what our expected Nyquist frequency should be based on based on the aliasing we expect. This is my 10 Hertz square wave. You can very clearly see the harmonics as well as the main frequency here being right at 10 as expected. The harmonics are very clear, and the graph looks very stable, very consistent. It doesn't gyrate. Here is a demonstration of my triangle wave being pulled at a 500 Hertz frequency and being output at 10 Hertz. The DC offset does seem to oscillate just a little bit, but that's most likely because of just, errors in collection here. Seems like the frequency most common is 10, right where it should be.